So if you're interested by the topic of decentralization as regards the energy transition and potential trade-offs with, let's say, a more centralized approach, I can assure you that you're at the just right place. My name is Jasper Geipel, working at the Energy Economics Group here at University of Vienna, and I'm hosting the session for the next 1.5 hours. I'm joined by 4 speakers, which you should hopefully see on the top of your screen: Vasu Katsiki, Da Huo, Nadia Ujan, and Gustav Resch. I'm sending a virtual applause to the speakers and also, of course, to the audience. Thank you for joining us. Before we delve into the topic, some necessary technicalities, even though I assume that you have already heard them quite a couple of times. This session is recorded and it will be made available via web later on. So if you want to recheck some things you've missed or skipped, you can check them out later. Of course, this does not affect you unless you are asking a question, in which case your question with your name on might appear on screen. During the session, we wish for your active participation, and you can do that either by raising questions or by participating in the polls. To do that, you can either visit the website slido.com and log in there with the code EMP-E 2020 and then go on focus group 7, or you can also use the QR code, which is shown on the top left, with your cell phone. Just use your camera, it should pop up, and then you still have to select FG7. It must be said that you can use the Q&A section during the whole time, during the whole session. However, the polls will only be visible and active directly after each presentation. If you want, if you are particularly interested by one of the questions, you can upload it, and so it's more likely to be raised. Content-wise, this afternoon session is structured as follows. We will have 3 short presentations that present insights from our own modeling activities and that tackle the question of decentralization from a different angle. Each presentation will be followed by a live poll where we ask about your opinions and a Q&A session. So without further ado, I would like to introduce our first 2 speakers, Vasu Katsiki and Da Huo, representing the MERLON as well as the Planet project. Vasu, Da, the floor is yours.
Hello, good afternoon. I hope you can properly hear me and you can see my screen. If not, please notify me. So, here with my colleague Da, we have the intention to provide some insights regarding 2 projects, Planet H2020 and MERLON H2020, in terms of how they contribute, let's say, to the transition of the energy system from a centralized to a decentralized future structure. Starting with a general approach, this transition towards a future energy system that is decentralized and comprises distributed generation and demand supply balancing mechanisms, as well as fosters competition and innovation. Certain, let's say, intermediate milestones are a requirement, such as complexity management, such as coordination of different energy networks, coordination of distributed flexibility resources of diverse types, and bridging of information and data exchange gaps. Okay. The two projects, Planet and MERLON, attempt to contribute to this transition. First of all, from the Planet's point of view, through a software platform for optimal network coordination and through deriving studies about policy reforms and standardization recommendation on an integrated energy system with coupled energy carriers. And from MERLON's point of view, through a distributed energy storage optimal planning and sizing tool that Guy is going to present later on, and through a distributed flexibility optimization platform for local energy systems. That is the, let's say, the focus of the operational side of the project. Actually, Planet responds to the need for informed decision-making on optimal pathways of utilization of local district-level flexibility resources for energy system stability under absorption of high shares of renewable energy penetration. Its contribution is through the form of a decision support system for planning operational synergies between different energy networks for energy flow optimization. The actual software tool that the project develops and will deliver is the Planet orchestration software tool that actually evaluates the potential of leveraging, let's say, the electrical network bottlenecks through flexibility provided from energy conversion units such as power to gas and power to heat technologies against the traditional solutions of grid reinforcement and expansion. This ICT system can be helpful, let's say, in order to create some validation of policy-induced impact. More specifically, the scope of networks within planets is three: the electricity, the district heating, and the natural gas network, and how they coupled through storage and conversion technologies such as power to gas, CHP, and power to heat, either in local or in central level. And last, the virtual energy storage technology that actually couples, let's say, a final use with the electricity sector. The focus is also on distribution networks, and the objectives is the maximum renewable penetration in the electrical distribution network, the minimization of expensive interactions from the distribution to the transmission grids through channeling, let's say, the energy flows from the electrical to the district heating and the natural gas distribution grids. And last, the alleviation, let's say, of the need of network expansion through optimal planning of the decentralized flexibility and its optimal utilization. Regarding the tool per se that we are developing and aim to deliver by the end of the project, we can see on the right, let's say, a schematic architecture that shows that the tool includes a network simulation engine, a central optimization and flexibility scheduling engine that actually coordinates certain asset models that are models of the conversion and storage units that are utilized and specified within the Planet framework, and actually an orchestrator cockpit through which the user, we can see here on the right, sorry, the user interface, through which the user can configure scenarios and register units and introduce specific cost parameters that are needed for the studies. The decision support system actually facilitates the assessment of the electrical grid balance and stability, the technical evaluation of different business models from concerning conversion and storage assets, as well as, let's say, the validation of different policies and the conclusion of policy recommendation for sector coupling. We can see here some other views of the tool. In general, it facilitates the configuration of different, let's say, energy scenarios that include the different energy vectors, configure different networks, the introduction of different time granularities in the simulation, and the configuration of distributed energy resources that are connected, let's say, to each node of the distribution system. It also facilitates the registration of conversion units through a special platform and the introduction of cost parameters in order to provide some insights regarding costing of different solutions. We have provided here 1 or 2 slides with some study that we have performed and some results. The study focused on the virtual energy storage technology, and actually the utilization and the utilization of the distributed demand flexibility for the optimization of energy flows. We tried to apply, let's say, the studies in pilot site of the project. That is actually in which a partner of the project is present as a local DSO. So we applied, let's say, the studies, we simulated and optimized the town, the distribution grid of the town of 1,110 end users that are connected to 31 medium and low voltage nodes. In this town, there is a high presence of renewables. The local production is the 30% of the total annual energy consumption, and it is intended to increase even more. Actually, 2 different scenarios we're studying. The one let's say, proposed a grid expansion in order to try to smoothen the, to perform congestion management and allow the introduction of further renewable energy penetration. And the second one, to perform an optimal demand modulation on local level, on district level, utilizing, let's say, context-aware demand flexibility forecast from a local demand, from local prosumers. So it came out that the total flexibility, let's say, potential demand flexibility potential of the area amounted to 38.5%, and which provided an available, let's say, demand flexibility that could be modulated that reached on an annual basis the 22% of the total demand. We applied the optimization scenario that combined the maximization of renewable absorption with an energy efficiency orientation in order not to increase the demand, in order to absorb, to be able to absorb the renewable production at real time. And the results were that for this network of Sorea in a town in the south of France, the reverse power flow was decreased with respect to the baseline scenario at almost lower than half. That there was a significant increase on the absorption of the renewable, the increase of self-consumption, and the coverage of the demand through the renewable, through the self-sufficiency vector, and all this without increasing and actually slightly decreasing the total consumption. This scenario was performed for 1 year. These results were applied for were calculated for 1 year of operation in the town of Saint-Julien in France, and we conducted a cost-benefit analysis that let's say attempted to monetize these two approaches, the baseline and the virtual energy storage flexibility optimization one, projecting the results on a 10-year basis and taking into account the trends for demand and renewable growth in the area based on realistic scenarios. Let's say the grid expansion infrastructure cost was compared with two alternative scenarios regarding the investment per se. In the first one, the DSO actually funds the entire decentralization strategy through installing the essential equipment to the prosumers for the flexibility extraction and control. Both solutions are similar in terms of being capex intensive. We see here that there's also not an optimal solution because the break-even is at the end of this 10-year cost-benefit analysis. And we see a second option here that actually compares the baseline grid expansion scenario with the cost for an alternative approach, the configuration of a local flexibility market, a local demand response market for local energy flow balancing, where the prosumers participate and their flexibility is optimized by the DSO. We have noticed that this is a more, let's say, cost-effective solution, and the benefits increased gradually through the years of the study. Apart from the cost per se of the two solutions, we examined other parameters related to avoided costs, such as the loss of value due to PV curtailment, the loss of value due to technical losses when the production is far from consumption, and the CO2 emission avoided costs when the, let's say, the consumption is based on renewables. Based on that, we have concluded that it can be a realistic and a profitable solution to have a proper aggregation and smart load clustering and utilize the demand flexibility offered in order to accomplish a decentralized system balancing. But we think that this has some prerequisites, such as the motivation of the prosumers, apart from the proper remuneration, in order to participate in such demand response programs. Such motivations beyond the availability and utilization remuneration that we have already taken into account in our studies, they include the possibly subsidizing the essential internet, IoT equipment, smart home equipment, in order to enable electric heating and cooling controllability, and to enhance the position and the importance of flexibility within, let's say, the Energy Performance Building Directive, possibly, and the SRI indices, etc. So now we are moving on to the MERLON project that examines, let's say, a solution connected to battery technology. So I will pass the floor to my colleague Da, which will present the solution. Thank you very much from my side.
Yeah, thanks so much. So hello everyone, this is Da Ho from Newcastle University. So I will continue with the presentation by introducing the MERLON concept. So the optimization in MERLON applies to multiple levels. Basically, it equips local stakeholders, including DSOs, energy cooperatives, prosumers with innovative and highly effective tools for the establishment of robust business practice to exploit their microgrids and dynamic virtual power plants as balancing and ancillary assets toward grid stability and elevation of network constraints. So, if you can move to the next slides, Masu. So here in our MERLON concept, we propose to. Sorry, just a second. Yeah, sorry. We propose to optimal planning and sizing the battery storage. And here we present the aims and scope in terms of one of our pilot sites, the Austrian Gussing pilot site. So the challenges from the perspective of the pilot site, specifically for the stream area, is firstly it has high penetrations of local distributed generation. Its incoming supply to stream area is vulnerable to failure on the energy goosing and wider transmission and distribution networks. The energy supplied by distributed energy resources is high, but unavailable in the event of a fault. And further, the voltage regulations is very strict. And according to the transmission regulations, the voltage should be restricted within positive and -2% compared with the nominal value. So this limits the opportunities for future renewable generation or low carbon technologies. And finally, it has the potential future opportunities via ancillary service markets. So the MERLON solution can meet this requirement, but planning and sizing activities are required. So in our work package of designing the planning and the sizing algorithms, well, firstly, we need to define the activities and its requirements. And firstly, we need to understand of this, understanding the system. So we will be able to model the system and hence to addressing all the constraints. And secondly, we need to have the predictions of how the system will evolve in terms of the renewable generation and in terms of the residential load. So we'll be able to plan the assets to cover all the evolve. And thirdly, we need to make sure that all constraints can be met, consider the uncertainty from the load or from the renewable generation side. And finally, we will be able to quantify the value, meaning that we need to properly design our sizing and planning algorithm so we could maximize the profits or maximize the system reliability. And then one of the important subjects is to understanding the system reliability. So firstly, the definition of the reliability in the electric networks is its ability to operate adequately and securely to supply the loads with fewer interruptions. And specifically for different consumers, from residential customers to industrial customers, their value of reliability are different. So we need to appropriately model them. And thirdly, and then we need to measure the reliability, and this could take many of years. So the appropriate model should be built. And the integrated local energy systems are more complex than the standard distribution systems. So because it can have multiple paths to transmit the power, and it's more like a small transmission system, so its modeling could be a bit complicated. And in order to address all the uncertainty and variability of system parameters, we need to employ some probabilistic method to evaluate its reliability. So by using the MERLON approach and improving reliability by installing the battery storage, we could see some different changing. So specifically for our two pilot sites, one in Austria and the other one in Spain, we could see that firstly the failure rate is reduced a lot for these two pilot sites, and then the repair time is increasing a little bit because the insertion of the battery storage, and also considering the charging or discharging actions. And thirdly, we could see that the loss of load expectation, or in other words, the annual availability of the two pilot sites reduced a lot. And finally, by observing the expected energy not served, for the two pilot sites, they are reduced a lot. So it could see a very high improvement of installing battery to increase the reliability. So then we need to specifically carefully design the optimal planning and sizing module. So this is important because firstly, the battery storage is capital cost is very high, and secondly, its future operating patterns are uncertain. And finally, the MERLON solution needs to strike a balance between certainty of achieving its goals and affordability. So the planning and sizing under uncertainty, it involves the modeling of battery degradation and also the trade-off between reliability and operating cost. So in order to deliver the planning module, we applied these chance constraints to restrict the battery state of charge with a known probability. So considering the uncertainty, so for example, here is the probability distribution of the load forecasting error. And by specifying the probability level of the chance constraints by 10%, this means that the battery storage will be able to address the 80% of the uncertain load forecasting errors. So this avoids the battery to spend more investment on the capacity to address the extreme cases of the 10% of the forecasting error. And the 10% of focusing error can be addressed by other devices. And in addition to use the chance constraint to restrict the battery state of charge, it can also restrict the battery availability, so linking the optimal sizing and network reliability. And then we have proposed a battery degradation coefficient. So this is a global wear approximated coefficient. So the degradation is a function of final and initial state of charge, and the linear representation can have a very high accuracy of monitoring the battery degradation along usage. And by implementing our planning and sizing study, we could get these results. So by changing the probability of chance constraints violation, so reducing from 10% to 0.1%, meaning that the battery will be more likely to address the extreme cases of load forecasting errors with low probability. It also means that the battery will have higher availability to improve system reliability. So by reducing the probability of chance constraint from 10% to 0.1%, we could see the reliability cost is reducing, but the operational cost of the distribution network is increasing. So this indicates that we need to find an optimal trade-off between the reliability improvement and operating cost. And the optimal trade-off is dependent on the reliability of the connection to the wider system and the value of loss load, meaning how the customers would value the reliability and how much they would like to spend on improving the reliability. And another result is that we're changing the level of value of loss load. We could see a different different level of probability to reach the trade-off between the between the reliability and operation cost. So reducing the reliability of the wider network forces the integrated local energy system to operate more conservatively. So reducing its ability to participate in energy and service markets, particularly if there are sensitive loads on the network. And yeah, I think that's all for the presentation. And here we have a few discussion points. Oops, sorry. So firstly, so the first point is the decentralized.
Thank you, Vasu. We have this actually as a live poll. So if you go on slido.com, EMP-E 2020 and log on there, you can see the following live poll where Vasu and Da have prepared a couple of questions where we would like to ask your opinion. So the question is, decentralized systems have the potential to, and then please choose your answer. I give 1 minute, 30 seconds. And apologies, I just heard that apparently the EMP-E website was down for a couple of minutes. Apologies if you could not log in for this reason. Da and Vasu, question to you. What do you think about those answers? Does this surprise you? What's your statement on this? By far, the two most selected options were that it allows that prosumers engage more intensively in the energy system. Do you see it similarly?
Sorry. Yeah, sorry. I think from my perspective, I mostly agree with the poll. So basically, the decentralized system we have designed for our system, the integrated local energy system, basically we will encourage more prosumers to participate in the flexibility scheduling. So it's basically could improve the profits and better manage the system operations. And one of another objectives in our pilot site is that we have a very high renewable generation penetration. So a well-designed decentralized system will be better accommodate these renewable generations. So basically, I agree with the pool.
All right. I think due to the time, we move on to the next poll. In the meantime, there was a question asked by Robbie Morenson. The question is that the tight electricity network specification was cited as a problem. Should the voltage and frequency bands be widened? I think the question goes to Da.
Yeah, I think so, because the voltage is only allowable for positive and 2% compared with the nominal value. So this is a very strict boundary. So, but this is the law according to the Austrian transmission system. Maybe it's possible to maybe advise the transmission system operator to maybe revise the law so it could have more like renewable generation penetrations, so to like be installed in the distribution system or transmission systems. So that's my opinion.
All right, thank you for your question. We move on to the next poll. So which decentralization strategy seems most promising and should therefore be prioritized in terms of regulatory incentives?
Just an interview.
Yes.
Yes, just an intervention on that. That is a question that we thought it would be very nice to receive feedback from the stakeholders that participate here, because actually Planet and MERLON, they study all those four forms, let's say, of decentralized energy storage, energy conversion, and flexibility. And it would be nice, let's say, feedback for us to see which seems to be the most promising one. The sure thing is that the battery energy storage systems are very powerful in terms of their possibilities and the responsiveness to the network needs. followed also, but of course, let's say decentralized demand supply balancing and grid balancing would require not a monopoly from the part of one technology, because each technology has certain restrictions to the sustainability chain. So overall, we think that it needs the combination, let's say, from demand response with demand flexibility modulation, the energy carrier coupling through the allowed interactions on distribution level of the electrical heating and natural gas network, the batteries, and let's say some integrated local clustering, let's say, of the networks that could be an extension of energy communities. So our opinion is that everything should be combined, let's say, to the extent that the enabling technologies are
Thank you.
available.
We are a bit short on time, so I have to interrupt
Sorry
you
for
there. But yeah, if you want, you can go back to her directly and discuss those questions further on, perhaps even in form of a one-on-one meeting you can schedule through our platform. We are coming now to the next talk by Nadia Ujjain, Senior Researcher from EDF. Nadia, the floor is yours.
Thank you, Jasper, for this nice introduction. And I now will talk about a case study we are planning to conduct in open entrance. So I want to give you some key points about this case study. And the objective of this presentation is precisely to collect your feedbacks in order to improve the scope of the case study. So I wish that the part dedicated to discussions will be highly interactive and dynamic. So the main issue of this case study is to evaluate the impact of decentralization of investments decisions compared to centralized decisions on power systems. More specifically, so the centralized framework is viewed here as the least cost case and is considered as a reference baseline. All resources are exploited in a common objective, taking advantage of geographic disparities. Decentralization is the natural trend we are following because it allows to enhance acceptance and active participations of communities in fully exploiting the potential of local flexibilities, such as heat, biomass, transport, and demand-side management. So the objective of the case study is then to quantify the impact of decentralization of investment decisions in order to provide some insights on relevant coordination mechanisms to recover some efficiency in decentralized systems. So to talk about decentralization, we first have to specify the geographic scales that should be considered in this study. So we have to define two levels, a global level for the entire system under consideration, and a local level defining the mesh at which decentralized decisions are made. So we may consider Europe as a global level, for instance, and her regions as local levels. Alternatively, we may consider regions of Europe as local levels. We could also consider countries. We could also consider, and this is what we will do in a first step in our study, France as local level and her regions as local levels. Because we have already all data to conduct the study in this specific case. So three variants will be implemented in this study, ranging from a completely centralized system to a fully decentralized system. Each variant is formalized as a specific mathematical problem. The first variant is the reference, the baseline centralized case. In this setting, central operator is minimizing the investment and decisions and operation costs of the whole system, such as to satisfy the supply-demand balance at each node of the grid, and in order to ensure some ecological constraints expressed, for instance, as a limit in CO2 emissions, or a minimum level of renewable penetration into the mix. So the second variant, called decentralization of targets, is corresponds exactly to the same optimization problem, except that ecological constraints are specific to each entity of the local level. This means, for instance, that each region has fixed her own target in terms of CO2 emissions or self-generation with renewables. And the third variant, called decentralization, full decentralization, is much more ambitious. It corresponds to a game where each player is a local entity which considers her own optimization problem. For instance, one region could decide her own investments on renewable resources and storage in order to reach a minimal level of self-generation. This of course assumes that there is some interactions between actors, and specifically the presence of a global actor that will ensure the possibility to satisfy a backup to satisfy the supply-demand balance at each time step. Okay, so as we have just seen, for each variant, some optimization problems has to be solved. And to do so, we will use Plan4U, which is developed in Plan4U's H2020 project. Plan4U will be used at each scale to perform optimization of investment decisions and operation costs for power system for the target year 2050. I want to underline two important limitations of this case study. First, we are not able to provide a trajectory of investments decision from 2020 to 2050 because the optimization tool is only considering the target year 2050. And more importantly, this case study is limited to computing investment in power system only. This is indeed a strong limitation since, as seen in previous presentations, there is multiple interaction in both directions between the electrical system and other sectors as heat or transport, for instance. However, these interactions are partially modeled in our study because at least in one direction, we will consider joint assumptions on other sectors as input to our model. So we will indeed rely on scenario provided by open entrance storylines for year 2050, which will give us some consistent inputs, such as the electrical demand per use, demand response potentials, and renewable potentials in 2050. Then Plan4U would output, after optimization, a quasi-optimal generation and storage mix and the grid capacities. And it will also give the investment cost associated to these decisions and the operational cost of the power system, CO2 emissions, marginal costs, and many other outputs. So in this case study, it is of course essential to be able to integrate the increase of flexibility needs due to variable renewable integrations. To this end, we will rely on Plan4U ability to take into account a refined description of technical constraints related to flexibilities, such as ramp-up constraints on power plants, network congestion with DC approximation of power flows, storage capacities, characteristics of demand response, and many other constraints. And besides, the stochastic framework of Plan4U will be able to take into account uncertainties which impact the variable renewable generation, demand, and inflows, which will impact the optimization of the hydro reservoirs. So Then we have the capacity expansion model that will iteratively call the unit commitment model by providing generation, storage, mix, and grid capacities, and the unit commitment will implement an optimal dispatch for each hour of the target year 2050. And then by iterative calls, we will converge to quasi-optimal investment decisions. So at the end, we hope to have many indicators. As I said, investment decisions, operational costs associated to this mix, the quasi-optimal mix, CO2 emissions for each entity, renewable curtailment levels, some prices also, which are interpreted via the dual variables related to supply-demand constraints. And we think it is also important to quantify the variability of these indicators by simulating. This is possible by simulating the operation decision on several scenarios with a plan for you. And with all these indicators, we will be able to compare these three variants, and we hope this will help us to bring relevant recommendations for coordination of decentralized systems. Okay, so now I thank you very much for your attention, and I'm looking forward for discussions. And I wanted first to begin the discussion by asking you three questions via Slido. So maybe Gabriel, you can open Slido. So the idea is to have your feedback to improve the design of our study. And then the first question I wanted to ask is which geographical scale should be considered in priority? I mean, if we have no constraint on the data available, because as I said, okay, so this is, it seems the first responses seems to be clear. And so regions seems to be the most important, clearly, for you. So the global level should be Europe, and the local levels should be regions and not states. So this is an important contribution, I think. This is okay. So I think I don't know how many. So we have 13 answers, but the answer is clearly regions. So it is consistent with our first idea, but this is the most difficult analysis to conduct in terms of data available. Okay, so maybe we can move on to the next question. So the next question was concerning the target, in the constraints we will set to each local or global level. Do you think we should consider targets in terms of CO2 emissions, the maximum level of CO2 emissions? Do you think it should be in terms of installed capacity of renewable resources, or self-generation of renewable resources? Okay, so here again, it seems to be CO2 emissions seems to be, it's moving. Okay. So installed capacity of renewable resources seems to be not interesting at all. This is clear. And we have the level of CO2 emissions that seems to be interesting. Okay, thank you very much for this answer. Maybe we can move on to the next question. So which indicators should be considered? So in priority as output for comparisons of the three variants. So the system costs, expansion and operation costs of the new system. CO2 emissions can be also interesting if it is not a target, which is already taken into account. Renewable curtailment level. Okay, so can wait. Network congestion levels or other maybe other indicators. Thank you very much for this contribution. So operation cost seems to be very interesting. CO2 emissions are the two first indicators we should look at. Okay, I think this is a first feedback for us.
Thank you, Nadia. There has been a question in the chat, and one other comment I would make is, if in the polls you signed for others, maybe consider writing it as a remark in the questions and answer section. So there has been the question by Diana Süßer, who asks, optimization for whom? What are about the benefits for citizens and regions by decentralized generation? Do you consider investments by citizens?
Yes, so the idea is that when we talk about local optimization, the idea is that the local level could be, for instance, a region or a community. So the citizens of a region are all together in a community and will optimize for their own benefit. So we don't consider the full decentralization system where each citizen is optimizing his own benefits, because in this situation we're talking about investment in generation, and so the smallest level we consider would be regions. I hope this answers the question.
I guess. There's another one by Luca Ferrari. How do you approach the local versus global optimal scenario? They might diverge somehow. They might diverge. This is the reason why we have to study, to analyze both. And then the question, so we'll have two scenarios, for instance, the local and the global one. We will observe that global optimization will give a lower cost than local optimization. And then the idea is to change some targets for the local systems, change some targets in order to push the local system to the global solution. This is the idea, to give the right targets to the local optimization system in order to drive it to more efficiency in direction of the solution of the global optimization. All right. Thank you, Nadia, for your answer, and thanks to Luca to your question. I think as it's already, as we are already a bit on time, I would switch now to our third and final presentation by my colleague Gustav Resch. Thank you. Gabriele, can you make me presenter? I will show the slides. Hope you can see it.
Yeah, thanks, Jasper. I think I take over now. Well, my name is Gustav Fresch. I'm here, same as Jasper, at the Technical University of Vienna. And topic of my talk today will be also in the field of central versus decentral, but I look now at the policy-making perspective. So the need for both would be already my conclusion, that we need policy making on both fields and we need coordination between that. And I will shed in my presentation light on the role of renewable cooperation. Content of my speech, first starting with an intro, then coming to a gap analysis where we look at the need for renewable cooperation. So in terms of national energy and climate plans, and we take on board then also the need for that, given that we might see there an increase in the ambition for renewable energies at EU level. We then take a look at the impacts of renewable cooperation and exemplify those for the electricity sector, and with conclusions I will end up my presentation. So next slide, please. As an intro, I would call it the road to glory, the road to climate neutrality at EU level. Throughout last year's EU member states have agreed upon 2030 energy and climate targets. You're all aware on that we have the targets of 32% renewables, 40% greenhouse gas reduction, and 32.5% energy efficiency, but they are all expected to be revised upwards because there is the European Green Deal on its way, and already the impact assessment, which has been published recently, reveals something like a 38 to 40% optimal, well, at least renewable share, what I took, and yeah, also the greenhouse gas target will move upwards towards 50 to 55%. In the past, member states, in accordance with the old target umbrella, have been asked to provide, however, their national planning, so the national energy and climate plans had to be submitted by end of last year. And what we expect for the coming decade is, of course, a strong increase if we look at renewables, then we expect a strong increase in the power sector, in other sectors, and that will create some challenge to the system, as we have seen also in the previous presentation. And also, since it's also the question of decentralization versus centralization, or however you put it, renewable resources differ across the EU. We think that cooperation between member states, or within a member state, cooperation between the actors is of key importance, helping to make promising rest potential in certain parts and areas available to neighboring regions and countries. And that would, of course, facilitate the overall energy and climate target achievement. What we then did in the study, and let me highlight now the AURES-2 project, where we look at auctions for renewables in Europe. And within that Horizon 2020 project, we from TU Wien are conducting a study on for example, the European or the cross-border renewable cooperation. And as part of our analysis here, we then took a closer look at national energy and climate plans, and aim here was to identify from that the possible role of renewable cooperation. you can see on that slide a summary of the national energy and climate plans that are available and where the countries aim for in terms of overall renewable shares by 2030. And you see in that slide also a comparison with the given 2020 targets. So the well-known 20% renewable EU share, which should then be increased to at least 32%. And if we sum up the national planned renewable shares for 2030, that would already bring us to an EU RES share that is higher than the agreed upon minimum target. So according to our calculations, we end up, the EU would end up with a RES share of approximately 33.6 percentage points if all member states manage to deploy renewables as planned. The renewables ambition, as you can also nicely see on the slide, differs, however, to a large extent between the member states. For example, one of the, as I would say, a little bit reluctant countries in terms of renewable ambition, one can look at countries like Slovenia, Romania, and on the upper range, so those that have a very high renewables ambition, you may look here at Spain, of course, Sweden, Denmark, that all plan for a major increase in their renewables share until 2030. So we took now that planning as a basis and conducted then a first, as we can say, check-up, a feasibility check-up done by modeling, where we also did some, on the one hand, dispatch modeling with power system analysis, and where we also looked at the necessary technology diffusion, at the investments, at the cost impacts. Least cost pathways had been derived, taking the given 2030 targets as given, and then we modeled here that the countries do that on their own, or that we would have here a cooperation across the member states. And modeling shows that without renewable cooperation, well, not all countries could manage to achieve their planned renewable deployment. But obviously with cooperation, where, how to say, the surplus in one country can be used in another, as we see it already in the 2020 context, the planned shares could be achieved. We see, according to this NSCP planning, only a small gap if we look at the scenario without cooperation. So it's 33.1 versus 33.6 percentage points. Next slide, please. Then if we take here also into account the increased ambition, so the, as we call it, the needs driven by the Green Deal, so the Green Deal needs, and we assumed here, even before the impact assessment was published, and how to say, a useful renewable share of around 40% in accordance with a 50 to 55% greenhouse gas target for 2030. Then what we then did further was to calculate some sort of fair effort sharing. We followed here the guidelines in the governance directive, where there's a sort of benchmarking system described. And if you follow that, you come to those target shares for 2030 in terms of where the member states should head towards, as highlighted here in green on that slide. At EU level, that means quite a significant increase, and also for certain member states, it means a quite significant increase compared to their planning. Exception from that is Spain, where their own planning was even above what we identified here as a sort of new benchmark. We then did the same feasibility check as we did it before for the NSCP targets, and without surprise, given the stronger overall ambition level, EU-wide RES cooperation would now appear quite essential for achieving the stronger RES uptake at short notice at EU level. So the gap that would now arrive is without cooperation, we would end up with a share of around 37 point something percentage points. And of course, with cooperation, well, it could be achieved, but yeah, that would require immediate policy action. We then summarize here what we identified in terms of a sort of gap analysis. So let me start it with that what is already not written in stone, but what is already clear if we take it from the aggregated perspective. So NSCP planning versus Green Deal needs. We see here a quite significant gap that might arise if you consider the already official NSCP, so the official national planning, with the possible increased ambition according to the Green Deal needs. So that would leave us a gap in size of 6.4 percentage points. So simply by subtracting from the 40% new EU target, that where the NCP planning would bring us to, so the 33.6 percentage points. A smaller gap can be identified if we assume further that member states will now have to revise their planning in accordance with the Green Deal agreements that are about to come. And then that gap might then be in the size of possibly a little bit less than 3 percentage points, so 2.6 if we follow here our modeling exam. And the figures taken from the modeling exam, they are shown in the graph on the left.